Hello, so today I'm going to talk a little bit about limits and how we find them. Now, when we think about it in terms of like limits, we have to consider that we're looking at possibly a function which may or may not be defined at some particular point. So let's say that this is like a, and then let's say that this point right here is L. So we normally will write that if we're looking at the limit as x approaches a for f of x, I say that it has to equal to the value that it gets closest to. Now, once we can decide that the limit value is L, for example, we have to look more further into this as it only equals to L if and only if you have that the limit from the left side of A is equal to L and you have that the limit as x approaches a from the right side, that has to equal to L as well. Now normally we'll just technically say that the limit as x approaches a for f of x equals L. We normally will use the statement if and only if the limit if and only if the limit as x approaches a from the left is equal to the limit as x approaches a from the right. I'll just put a plus sign. And of course, we would have to say that that equals to L. Now, with that, this tells me that I need to establish that what are the different ways that we can find any limit then? Well, the first is the easiest. It's through the graph. The next is that we would have to use what is called a table. Now, the other way that we can use this is through what we can say like algebra. And then another way that we can find the limit is through what we call analytic methods. So let's kind of just look at how we can find a limit just from a graph. So for example, let's say that we have an equation and let's say that we have that the equation looks something like this. And then we'll just say, for example, that the function looks something like this. So we'll just say, for example, that this is going to be equal to 1 perhaps, and then we'll just say x and y. Now, what we'll do here is we'll just put that based on this scale that we'll just put 1. So if we're trying to find the limit as x approaches 1 for f of x, well, first we have to look at the limit as x approaches 1 from the left side. Well, I have that based on my graph. I have that if I follow along from here to here, that it's going to approach the value 1. But I also have that if I look at the limit as x approaches 1 from the right side, well, in this case I have that I'm looking at it from the right and it's approaching the value 1. So we'll say that that equals to 1. Now, together, this means that the limit for the function f of x as x approaches 1, we have that that's going to be just 1 as well. Now, if I would have, let's say perhaps, if I would have used the function that defines that graph to the left, then you would have to basically just say that if we knew the function as f of x equals to negative the absolute value of x minus 1 and then plus 1, you can kind of see that, yeah, if we plug in values that are less than 1 or even greater than 1, it's going to roughly approach the value 1. So in that case, you have that it's just 1. Now, the other way that we can look at this, and this was using a graph. The other way of which that we can also look at this is, for example, what if we were to use like a table? So let's just say that we're trying to find the limit as x approaches 4 for the square root of x minus 2 all divided by x minus 4. Okay, so we want to figure out what this limit is. Now, note that if you plug in the value into the calculator or into this equation, you'll figure out that that's basically going to give you 0 over 0, which is what we call indeterminate. So this means that we would need to rewrite, we could either rewrite the equation or just make a table. Let's just make a table. So for instance, we have 4, we have 4.0001, we have 4.001, and then we have 4.01, and then we have 4.1. And then furthermore, we have 3.999, and I think that would be an extra 9. Yes, we have 3.999, and then we have 3.99, and then finally we have 3.9. Now, we would basically have to figure out, we would basically need to figure out like the expression. So like if this is y, then we just need to figure out like what's the corresponding y value as it relates to each of these x values. Now, what I'm going to do here is I'm just going to, let's erase this a little bit and move it down a little. Now, the 4 is the one that's undefined, so we actually don't know what that is, so we'll just put undefined. Now, we need to figure out roughly like what is 3.9. So if we do that, we have the square root of 3.9 minus 2 all over 3.9 minus 4. Now, if we do this, it's going to give us an approximation. So for example, like we have, let's see, okay, so we have the square root of 3.9, and then we're going to do minus 2 divided by 3.9 minus 4. Okay, so let's see. Okay, so we'll do it like this. We'll do the approximation. Man, these get a little tricky. Okay, so I get that the approximation for this one is 0.252. Okay, so that's 252. Okay, now you want to try 3.99. So why don't we just go ahead and use our same computation, and I'm just gonna change it to 3.99. Now you're gonna start to notice that there's a bit of a pattern, like you get 0.2502. Furthermore, you're gonna repeat this process until you find all of the values that give you the approximation for the limit. So here's what we'll do. We're going to input the remaining. Okay, so we have that if we do 3.999, we have that that's going to be 0.25001. And then if we plug in 3.999, we get that there's going to be a couple zeros in between, so this is going to be 0.251231. Now we want to do the exact same thing with regard to 4.0001. So 4.001 is 0.24 or 0.25. No, it is 0.24. So we have 0.24, 24, and then we have 3 nines. Now if we do similarly, we're going to find that essentially there is a bit of a pattern that you have that's going to be 0.24998. And then furthermore, we'll do the last ones, 4.01, and that's 0.2498. And then finally 4.1, and that's going to be 0.2484. Okay, now the main thing for this is that we can see that based on this approximation, we should be able to say that the limit as x approaches 4 from the left, we have that that's going to be approximately 0.25. But we have that the limit as x approaches 4 from the right side is accordingly also 0.25, which actually means that we can conjecture that the limit, so we can conjecture that the limit as x approaches 4 for f of x is equal to 0.25, and that's it. Okay, so in this case, we can see that, okay, yeah, if we're going to do the table values, we just have to be very close to 4. Now, the other thing of which that we can look at, for example, is how do we solve a limit problem? So we have the limit as x approaches, let's say 5, and we have x squared minus 25, all divided by x minus 5. Now, I still have that if I plug this in, I get 0 over 0, which means that essentially we can just rewrite this in the following manner. Let's actually go ahead and just say that, well, if we're trying to find the limit as x approaches 5, we just have to factor the top as x minus 5 and x plus 5. So that means that we have x minus 5, which this happens. We have that cancels out. and it tells us that we have the limit as x approaches 5 is x plus 5, which if we take the limit as x approaches 5, well, that's just going to be intuitively 5 plus 5, which is equal to 10. Now, you could go through the process of making the table, but you really don't have to. Now, I mean, for here, we said that, okay, well, if it's indeterminate, we just need to rewrite it or just use the tables. So notice that if we went back to our example of f of x equals to the square root of x minus 2 divided by x minus 4, if I was to, let's say, multiply by the conjugate, okay, so if we multiply by the conjugate, we have square root of x plus 2 divided by the square root of x plus 2. Well, when we multiply this through, we're going to get x minus 4 all divided by x minus 4, and then we have the square root of x plus 2. So we can see that this is basically going to tell us that that cancels out, but it reduces down to, okay, so it reduces down to 1 over the square root of x plus 2, which means that if we were to look back at our question about taking the limit as x approaches 4, then in reality, this is the equation wherever it's undefined at 4. So what this tells us is that, okay, so you have 1 divided by the square root of 4 plus 2, of which is just 1/4, which is the same thing as 0.25. So we see that we can get the answer if we rewrite it or if we use a table, which is, either case is the same thing. Okay, now the next step, or the next thing that I would like to show you is, for example, like what if we don't have a function of which is defined? So for example, if we have the limit as x approaches 2, and for example, if we have x plus 2 divided by x squared minus 4. Now, this is a little special because, for instance, I know that if I rewrite this as x plus 2 divided by x minus 2 and x plus 2, well, I can see that basically this is going to cancel out the factor of x plus 2, which basically means that the function reduces to 1 over x minus 2. But look at this. If we end up with that, then that means that we're taking the limit as x approaches 2, and we have 1 divided by x minus 2. Now, if we plug in 2, we get 1 divided by 0, which is undefined. But in either case, because we did not get a real number, and this is undefined, it basically just means that that this problem does not exist. So we say it does not exist. Now, more or less, you do have some justifications of, like, why is it does not exist? Well, if we were to look at the graph of the equation, we would see that essentially that there's a vertical asymptote at 2, and you'd have that the graph of the equation would look something like this. Okay, so in this case, we have something that looks like this. But if you kind of look at it, you would see that, okay, well, the limit as x approaches 2 for f of x from the left side, well, it tends to what we call negative infinity. So it's negative infinity. But then you have that the limit as x approaches 2 from the right side for f of x, that goes to positive infinity. Now, by this logic, this doesn't tell us exactly where it goes in terms of the behavior, but because these two are both different from each other, then really that's enough to say does not exist. Okay, so as you go through the process of limits at infinity, just look at the behavior of the function, like where does it go to? Because here I have that it's just decreasing, and over here I have that it's just increasing. So in this case, like the limit cannot exist. Okay, now a better way of showing this, for example, like for instance, like when a limit does not exist, is if I have the following, like f of x is equal to 1 for when x is greater than 0, and -1 for when x is less than 0. If you look at the definition, or like the graph of the equation, you're basically going to find that the equation, it looks something like this. So you have that this is 1 and this is -1. But if you have the limit as x approaches 0 for f of x, it does not exist. Mostly because you have that as you look at x from the right side for f of x, it's equal to 1. But then you also have that if you look at the f of x and you're looking at the limit as x approaches 0 from the left side, you're going to get -1. So in this case, both of these two, it tells you that the limit as x approaches 0 for f of x, it does not exist. So more or less the exact same process. You can either just look at if there's a jump, you automatically know it does not exist. Now the other thing of which that you will look at, for example, is how do you find the limit. Okay, so how do you find the limit of a problem where you're approaching, let's say, positive infinity? Okay, so let's say that you have x divided by x squared plus 1. Well, one way to look at this is that, for example, for instance, we know that if you're looking at a function, like say for example 1 over x, well, the limit as x approaches infinity for 1 over x, that goes to 0. But similarly, if you have, for example, 1 over x squared, you have that the limit as x approaches infinity for 1 over x squared, it still equals to 0. So that's more or less like telling you that 1 over x to any power goes to 0. So let me show you how we can do this. So we have to divide by the largest largest term in the denominator. So that would be x divided by x squared divided by x squared over x squared plus 1 over x squared. If we go ahead and we do it like this, then that means that we end up with the following. We end up with 1 over x, and then we end up with 1 plus 1 over x squared. Now, if we apply the limit operator to both the numerator and the denominator, then technically that's going to give us the following. It's going to give us 0 for the top part divided by, well, the 1 stays constant, so that's 1, plus 0, but that's still just 0. So we have that the limit is just 0. Now in class, normally I would probably just say that this problem is bottom heavy because the bottom part goes quicker to infinity than the numerator. So in that sense, we have that this limit must go to 0. But if you had that, for example, it was the same. Like if you had the limit as x approaches infinity for x squared over x squared plus 1, this would go to 1. Why? Because it's kind of like you're saying x squared over x squared equals to 1. So they're the same. But if you had the opposite, like the limit as x approaches infinity, and you had x squared plus 1 all over x, well, this is going to go to either infinity or negative infinity, depending on not only where x is going to, but like if this is preceded by a negative symbol. So in this case, you would have that this would go to positive infinity because you have that the top part goes to infinity and the bottom part goes to infinity. So it's kind of like saying that you have x squared over x and that goes to x, but then that just goes to positive infinity. Or look at it this way, infinity over infinity, but that's a little weird when you think about it like that. So in either case, like you could always say that it's going to be plus or minus infinity depending. Technically, you can do that the exact same way where you end up with x and then you plus 1 over x and then all of this is divided by 1. So in this case, you have that that's just going to kind of like infinity plus 0 divided by 1. But again, that's a little weird to say it like that, but it is one way that you can say it. So it tells you that, yeah, you're going to positive infinity. But it's probably just better to look at the ratio, like to say like, okay, I can see that the top part goes to infinity and the bottom part goes to infinity, but yeah, it'll kind of make more sense like when you kind of like map it out in either case. Um, okay, so be sure that you do look at some of the different types of limits, whether it's, just using algebra or using the graph or using some numerical analytic methods. Okay. And there's always desmos.com in any case, like to check your work.